Okay, maybe we should get started since there's no more seats available. It's a pleasure to welcome our colleague, Rob Schoelkopf, Sterling Professor of Applied Physics and Physics. Rob first came to Yale in the mid-1980s to a Science Saturdays program that Bob Wheeler and Werner Wolf were showing off liquid nitrogen and low temperature things, and Rob got hooked. He got his undergraduate degree at Princeton, where he did his junior paper with Bob Dickey, and he got hooked on measuring quantum noise. He went to Caltech and worked with Jonas Muizinus, building detectors for radio astronomy, and then came to Yale as a postdoc with Dan Prober in 1995, and invented the radio frequency single electron transistor, the world's fastest counter of the smallest beans, as the Yale press office called it. And on the strength of that, became an assistant professor in applied physics, and has been here on the faculty since 1998. He's going to talk to us today about the 2025 Nobel Prize in Physics, which was shared by our colleague Michel Devoret, and its relation to the quantum mechanics and quantum optics of electrical circuits. Rob.
Great. Thanks, Steve. Can you folks hear me okay? Okay, good. I don't hear it so much over here. Right, so thanks, Steve, for the introduction. Thanks, everyone, for coming. It's been a kind of an amazing year, right, in a lot of respects, but especially to see this field that we've been working in and developing around the world, but especially here at Yale, sort of recognized with this well-deserved prize. I see, I have to do like this. And there's the short form of the citation. The prize was given to John Clarke, Michel Devoret, and John Martinis. John Clarke was an expert in superconducting devices and squids on the faculty at Berkeley. Michel was then a postdoc in John's group, and John Martinis was the grad student who worked on the experiments together. So one of each of the levels of folks there. And it was given for work that's almost exactly 40 years ago. And so what I wanted to do today, I wanted to make this kind of fun, hopefully accessible for students of various ages. I see even some of the students who are taking the new course we've introduced, which is a one semester mezzanine class that's for advanced undergraduates and beginning graduate students on this field of superconducting quantum circuits. So hopefully that'll be all something that you guys find entertaining at least. So you'll get the one semester version and then also the 1 hour version. Also wanted to say thank you to this triumvirate. Between Steve, Michel, and myself, we've had an incredible time and so much fun discussing physics and exploring this playground over the past 20 years. And also, they've generously donated. I've cribbed lots of slides from both of them. So the sort of origin of our field kind of goes back to one of the most basic and sort of enduring questions about quantum theory, which is, how come we're not intuitively used to things like superposition and entanglement? Why is it that the macroscopic world seems to be obeying different rules than the world of single atoms and single photons? And that goes back, I'm not sure if you can see the picture here. This is a little chalk sketch of a cat in a box with a gun that's breaking a poison vial. It's Leggett, Tony Leggett here, discussing Schrodinger's cat, which was originally, of course, put forward as sort of a reason why the early proponents of quantum theory thought, well, this can't be the whole story because this is clearly ridiculous. We can't have macroscopic objects that are actually in a superposition or entangled with some single degree of freedom like an atom or something like that. But what Leggett did starting in the early 80s was he had a series of papers that were somewhat philosophical in nature, in which he pointed out that there were macroscopic quantum phenomena like superconductivity or superfluidity in liquid helium that have macroscopic manifestations of the fact that they are quantum fluids. So in a superconductor, you can have a current that flows in a loop forever. In superfluid helium, you can have a circulation of a fluid that goes around a pipe in principle forever in a frictionless way. But that those weren't quite macroscopic in the same way that Schrodinger's cat was. And he started speculating that maybe these superfluid or superconducting systems would be a good way to test the kind of limits of quantum mechanics and how macroscopic an object or a system could one actually have that you would observe these explicitly kind of fundamental, weird and spooky, whatever adjective you want to use, manifestations of quantum mechanics be present. And he didn't talk so much about this one, but here's an example of a simple electrical circuit, the familiar LC resonator, which has a single degree of freedom. It has two variables, the current and the voltage, or the flux and the charge on the capacitor. And the question is, are those two variables actually in quantum mechanics non-commuting, and they're going to have manifestations like zero-point fluctuations and all that other sort of stuff. Could we actually observe the kind of phenomena that are associated with single atoms and the like with this kind of system? Now, why would that be similar to an atom, and why would it be different from an atom? So Michel has a slide that he's used for many years that's sort of comparing and contrasting real atoms with electrical circuits, or we're going to call them artificial atoms in this talk. In a real atom, you have an electron, and if you have an excited state, maybe the electron has some motion. This is, again, very hand-wavy, but there will be quantum phenomena associated with this atom. It's all very clear to us now. If we excite this electromagnetic resonator, you will have something where charge is also sort of sloshing back and forth, right? You have charge accumulating on the pads of the capacitor, and then current running back and forth through the inductor. And it's all sort of held in place. There's a restoring force associated with the ion core and so on. But it's a very different kind of system. It's a very different kind of phenomenology, right? In the hydrogen atom, we're used to thinking of this as being inherently quantum. It's composed of two elementary particles. It's a very simple and very small system in that regard. And we have things like the velocity and the force that we can understand and in some sense probe, but those now become things that are ordinarily not something we think of as being quantum mechanical. Things like the current through the inductor or the voltage on the plates of this capacitor. Now, if we say, okay, why make this out of superconductor? One reason is we want to prevent dissipation, because that will help preserve the quantum behavior for longer. But also, we want to have something where we can make some observations and have it behave a bit like an atom. Oh, and one other important difference, of course, is the scale. So, typical hydrogen atom right on the angstrom scale. One of these LC circuits that we can make is on the scale physically of millimeters. And also, we can do things like paste them down and attach wires to them and do stuff, nasty stuff to them that you can't do with real hydrogen atoms. However, there's a real problem if you try and just take a simple LC oscillator and use that as your atom, or try to observe explicitly quantum mechanical behavior in that. And the reason for that is that an LC oscillator is a very linear system. Okay? That shows up, for example, in the energy spectrum. You might have this parabolic potential, but you have equally spaced energy levels all throughout. And if one takes this system and you push on it, if you try to control it or manipulate it using a classical field, this system will always be in the correspondence limit. So you will push it around. It has a position and a momentum, or a current and a voltage, but the sort of center of mass of those variables in phase space is always going to follow exactly what a classical system would have done. The only real difference is that, if you could get in and look at zero temperature, there'd be some non-zero fluctuations. The position in phase space is a little bit fuzzy. There's a bit of a fuzzy ball associated with the position and the momentum, or the charge in the phase. But that's very difficult to observe. And so to make something that's more like an artificial atom and allowed our laureates to actually observe the first evidence of macroscopic quantum effects and energy quantization in circuits, you needed to add a very important ingredient, namely the Josephson junction. And a Josephson junction is nothing other than a sandwich of two superconductors with a thin insulator that allows tunneling of charges between. The microscopic understanding of superconductivity came to us with the theory of BCS, Bardeen, Cooper, and Schrieffer, in 1957. And Josephson, interestingly, in his PhD thesis, if you're not aware of that, proposed his effect. What Josephson's equations are is it says that, well, there's going to be a current that can flow between these two electrodes, and it could be measured using voltmeters and forced using current sources and the like. But that the current through this element will be a sinusoidal function of the phase difference in the two condensates of the superconductors that are making up the two electrodes. And so this sinusoidal current it's like an inductor, but it's a very nonlinear inductor. In addition, the other one of Josephson's equations says that if there's an actual voltage imposed, there will be fluctuations of the phase that happen at a characteristic frequency given by these fundamental constants E and H. But the sort of so-called resistively shunted junction model, the sort of behavior of a circuit like this, is ordinarily also pretty classical if you're not striving to make this system be in a very special realm of parameter space. And moreover, this sort of variable here, phi, is the phase difference between the order parameters in these two electrodes, but the behavior of that variable now, except for the fact that it has this sinusoidal behavior and there are E's and H's in some of the relationships, is almost fully classical. And for example, if you want to understand the dynamics of this kind of circuit, just a simple Josephson junction that is biased with a current, you can write down these so-called RSJ model here, which is basically just a version of Newton's laws of motion. It's a second-order differential equation, right? That's just fully classical, again, except for the appearance of some interesting fundamental constants as prefactors. And what this model says is that this sinusoidal current phase relationship of the Josephson effect gives a kind of potential which is like a cosine. It's got an oscillating or undulatory component. And then if we add the addition of a bias current, we can kind of tip this potential, giving us the sort of tilted washboard potential that's shown here. And what one can do with this, for example, is you can apply a current and measure the voltage. And you can say, well, OK, what am I going to observe if you apply a current that's less than the critical current? You will just have no voltage that develops. But if you apply a current that is somewhat greater than the critical current, then this particle is not bound within one of the wells, and it can run down this washboard. This variable phi here, again, is the phase difference between the two, but the derivative of this is basically the voltage. So in that case, we have something approaching a constant velocity, so there's a constant voltage developed across the junction that you can measure. And there are still these undulations, so there will be some oscillatory component at a very high frequency of 484 gigahertz per millivolt, which is 2e over h. This was sort of understood and studied somewhat in the sort of 60s and early 70s, late 60s, early 70s. And this Josephson junction turns out to be the kind of nonlinear thing you need to make an artificial atom, or to make something which is going to display really explicitly quantum behavior. And the way this works is you have to get into the right realm of parameters. So the first thing you need to do is have the frequency of small oscillations here be larger than the temperature. And if that's going to be typically a few gigahertz, that corresponds to something like 1/4 of a degree. So you need to cool this system to very low temperatures, lower than the temperature of liquid helium at which the sort of RSJ model was initially explored and all that sort of stuff. You need something called a dilution refrigerator, which can get your chip down to something like a few 1/100ths of a degree above absolute zero, or 20 millikelvin. And for those of you who've seen sort of popular press things about quantum computing and so on, the visual meme for a quantum computer is this big round thing with a chandelier-like set of gold-plated copper temperatures that you anchor things to, many wires coming in. This is the Berkeley refrigerator in which the Nobel Prize work was done. Is about that big in diameter, not this big in diameter like a modern refrigerator. And it had exactly one microwave input line, and all the measurements were at DC. Whereas, things you will go down to Becton and see cutting-edge academic experiments that now have, of order 100 lines of microwaves both in and out, okay? Because we're doing much more complicated things. An also fun thing is the state of the art of lithography. It was a niobium lead indium, so lead and niobium are both, and indium as well actually, are all superconducting elements. The lithography was done, I think, probably with RubyLith or something. The characteristic size scale is 10 microns, which is kind of small, but from the point of view of lithography in the modern era, not small at all, right? It's a typical Josephson junction in modern qubits is something like 0.2 microns on a side, so a good bit smaller. The other thing that you see here is kind of funny. This, in a lot of the popular things about the Nobel Prize, some actual image or cartooned image of this thing was shown. Most of what you're seeing here, these interesting tubes, are basically just specialized filters that were developed so as to remove all possible thermal noise or external microwave radiation from getting to the junction and making it go poof before you wanted it to. And so these so-called copper powder low-pass filters here were one of the innovations that were needed to get to this point. And so what Clarke, Devoret, and Martinis were able to do is take a small Josephson junction, put it in this dilution refrigerator apparatus, cool it down to a low temperature, and examine the dynamics of this washboard potential in the quantum regime. And in particular, if we have a washboard potential and a bias current that's applied, which is maybe a little bit less than the critical current, so the particle's not going to run, it's going to be trapped in one of these wells. If we take this quantum stuff seriously, right, there should be quantized energy levels in here associated with some energy level spacing that's corresponding to h bar times whatever the frequency of small oscillations are. And the important thing here is that this is now not a parabola. It doesn't give a linear system. It gives a system with some interesting nonlinearity. These energy levels are not equally spaced. And moreover, there are ways now to kind of measure various effects in this system. So one of the things you can measure is the fact that if you've tilted this washboard and you sit around and wait, and there's a finite temperature, you can be thermally excited up this set of energy levels and tunnel across, developing a voltage which can be measured. And that can happen by thermal activation, or if you're at very low temperatures, it can actually happen quantum mechanically, even though this particle is sitting here and it's below the energy of the barrier. There's some finite probability that you can tunnel in quantum mechanics through or under a barrier and also get to the voltage state. And that should manifest itself as sort of an escape rate into this voltage state that is independent of temperature. And so the first sort of signature result of the prize from 1985 was there were a pair of PhysRev letters that were just a few weeks apart. The first one shows this, which is basically the escape temperature. It's basically a linearized version of the tunneling rate, where we would expect from thermal activation an Arrhenius law, so this sort of temperature versus temperature being linear is like Arrhenius activation as a function of the temperature of the refrigerator. And then you lower the temperature down, and it sort of looks like the temperature is too high, with a particular value here, which is h bar omega over k. Now, it's worth noting that there were other folks working on the Josephson effect and looking at the limits on critical current in various kinds of small junctions, including a group led by Rich Webb at IBM Research that were doing very similar experiments. They didn't quite have the control, and they weren't quite able to observe things convincingly, because you see, this is a little bit like there's too much noise. So how do I convince you that this isn't an experimental flaw, that as I've lowered the temperature of the cryostat, the refrigerator everything's attached to, maybe my payload wasn't quite getting cold? Well, one way is they had a different junction with different electrical parameters that was supposed to follow a straight line, and it went down lower. But the real smoking gun of quantum behavior in this set of experiments comes in the second paper, where they used that one microwave line, and they were able to do a crude version of spectroscopy. So again, what they looked at was the escape rate, the sort of probability that the junction develops a voltage all of a sudden, as a function of both bias current and different frequency microwaves that were applied. And in the presence of microwaves, you would expect that you can resonantly promote the system to a higher level where it's closer to the top of the barrier and it can tunnel out more rapidly. And as you see here, there's a series of peaks, not very sharply defined, but they do kind of correspond to the energy levels within. And so this is the first observation of kind of energy quantization in a man-made artificial device with, okay, it was only 10 microns on a side, it wasn't millimeters, but the wires and everything attached to it are millimetric in scale, not sub-nanometer. So there you go. That gets you a trip to Sweden. But more excitingly, right, this is the first thing that sort of says, hey, we take these ingredients with Josephson junctions, we can have a artificial kind of laboratory. We can have a system where we can engineer things, we can make electrical measurements, we can maybe even control things in an interesting way, and have some of the inherently, most quantum of effects be visible. And also interestingly, at this point, there was about a dozen-year hiatus. So these experiments were sort of done. There were not a lot of immediate results that followed. A lot of the community that was studying quantum effects in the solid state was looking at the coherence of individual electrons as they move through solids or metals or semiconductors, or looking at the charging effects when you have a quantum dot or a very small piece of conductor. You are only able to add charges one at a time, and you can't add them if it's energetically too costly. And so there was a lot of people looking at these sort of other effects, not the Josephson effect in its kind of quantum guise. But what these experiments told us is now we had a sort of toolbox for making interesting circuits. And that toolbox should have no resistors. It's allowed to have capacitors, which are lossless if they're superconducting, Josephson junctions, which are hopefully lossless if they're superconducting, and regular inductors, linear inductors, you can use as well. And this toolbox became a lot more interesting when we got to about 1998, and Shor said, maybe a quantum machine can factor numbers. And maybe there's something different about, Shor is 1995, I beg your pardon, but the sort of first results are following in just a couple years after that. People started saying, well, wait a minute, maybe we can make something which is an electronic device that can actually function as a qubit, a quantum bit of information, and maybe we can store and process information in these superconducting circuits in a way which is really quantum. And then comes a big flurry of activity, which I think I'll try and use the remainder of the time to kind of give you a lightning tour through. The Nobel Prize, again, should appropriately be given for the seminal work that establishes a direction of research or a field. But then, of course, the real payoff is when that leads to interesting places, right? And that's why it sometimes takes 30 or 40 years for one to know what's a Nobel Prize-worthy result. So one can do lots of interesting things with this toolkit. I won't have time to describe all of these by any stretch. This is from a paper that Michel and I wrote a few years ago, which Michel likes to call the Mendeleev table, the sort of periodic table of artificial atoms. If you have just junctions, capacitors, and inductors, there's sort of a couple of different axes that you can define that tell you how to characterize one circuit and distinguish it from another. It's not discrete, of course, like the periodic table for real elements, because you're not adding protons one at a time, but rather it's kind of a continuous diagram where you can engineer and tailor these things by how you make your fabricated circuit to give you kind of continuous range of these parameters. And Why lots and lots of different kinds of qubits? Well, because in the beginning, people were exploring a lot of different directions and also looking at ways to avoid some of the mechanisms for decoherence like charge noise and flux noise, which the experts in the audience know about, but just there are problems that are technical and you want to get away from them. Okay, so the sort of simplest and first superconducting qubit after the MQT results, which are really a qubit in themselves, of course, just wasn't thought of and called that way, is something known as the Cooper pair box. It's just a single Josephson junction, but not current biased, rather it's charge biased. So there's just a capacitor and a static voltage applied. And there were early measurements by the team, including Michel, who was then in Saclay, measuring the charge on this device. This has two states that are basically plus and minus one extra electron on this little island here. And you can measure the quantum states of that using an electrometer like this RF-SET that Steve mentioned. This was done with a low-frequency electrometer, just looking at the average properties. In 1998, which is what I was thinking of, Jack, is sort of the first operation of a superconducting qubit by Nakamura and Sai and co-workers in Japan at NTT. What they were able to do was observe the first Rabi oscillations, or maybe it's the Larmor precession. Where's Kurt? In this system, you basically apply a sudden pulse in the voltage. Now you go to something where the Josephson energy is coupling together plus and minus one electron. One additional pair is oscillating back and forth. And so this is their plot as a function of sort of the voltage you apply and the time you apply that voltage for that shows oscillations between the two states. So this is now beginning not just to look at the spectrum or where there are energies that correspond to specific states, but actually, halfway along one of these is creating a superposition where you're in both this little island of the Cooper pair box is in both 0 and one additional Cooper pair at the same time. The first Yale qubits were experiments that we did in collaboration with Per Delsing and his team in Chalmers. The first author was one Conrad Leonard, currently then at the time was a postdoc in my very new lab. And we basically took this same experiment where there's the Cooper pair box, here's that one island, here's the electrometer that sits next to it, and using this radio frequency single electron transistor, we could make more precise measurements of the states. Here's us doing spectroscopy. At the time, the line width was about 1 gigahertz. Those of you who work in the labs today know, like, oh, hey, it's not a bad qubit. The line width is 20 kilohertz or something, so that's progress for you over a couple of decades. But one of the things that could also be done in this experiment is we could abruptly turn the microwaves off, which are creating some population imbalance between the ground and the excited state, and look at how fast the signal recovers. And what Conrad and Leif and company observed was that this time constant here, that's not the most beautiful T1 curve for also those of you who are out there practicing, but that's what we were able to do in the very first experiments, was like a microsecond. So, if in this Nakamura experiment here, he's doing operations that are changing the state in a few hundred picoseconds or a fraction of a nanosecond, in some sense, this microsecond is already long. It means you can create something that lives for 1,000 times faster than you can manipulate it. If you want to build a quantum computer, you need to be able to manipulate things many, many times. There are other kinds of qubits that were also investigated. There's the kind of electromagnetic dual of the Cooper pair box, or the RF squid. There's the 3-junction version of the squid. This was also studied. And interestingly, Tony Leggett always seemed to think that the flux version of this was much more macroscopic than the charge version. This is a slide from Yasu, I guess. I'm not sure what his point of posing that question was. But there were other innovations that followed rather rapidly, and I'm going to now speed up a little bit because I've been waxing eloquently a little bit too much. But One of these was a device called the quantronium, done by Michel and his co-workers, again at Saclay, just about the time when he was moving here to Yale to join the applied physics department. What this device did was it actually operated at this kind of point here, which in terms of like sort of the energy landscape and those control parameters that one can have that change the energy level splitting, it sort of operated at this special saddle point, a kind of sweet spot where you're first order insensitive in terms of the frequency varying with noise in your control knobs. The atomic physicists call that a clock transition when you're insensitive to the variations in the laser power. With that, they performed the first T2 measurements, or measurements really of the lifetime of a superposition, doing a so-called Ramsey experiment. And we're able to see that the coherence of the superpositions was preserved actually for a very long time of hundreds of nanoseconds, up to even approaching a microsecond again. Another innovation in terms of the circuit landscape or zoo of qubits was the so-called phase qubit, introduced by John Martinis and co-workers then at NIST Boulder. John later moved to Santa Barbara, and then again sometime later on to Google in Santa Barbara. This phase qubit was basically just the macroscopic quantum tunneling experiment revisited. So it's a single large Josephson junction that's current biased. You drive here and use the first two states as the quantum bit, and then you can use a pulse of microwaves or a DC pulse to read things out. At the time, this gave very good performance as a readout, but very destructive and not actually that good at preserving coherence overall in the system. It was rather sensitive to that current bias and stuff as well. Also, in the early 2000s, 2001, I guess, Steve moved here to Yale, and we began this many years thrilling and engaging collaboration. And one of the things that we actually talked about in our first meeting in my office, I think maybe I was just joined the faculty, was that these systems also had nice analogs with systems in real atoms in atomic physics or quantum optics. There's a very interesting sort of platform known as cavity quantum electrodynamics, where you have individual atoms that couple to single modes of the electromagnetic field. That can be done with real atoms in the optical, and what we kind of proposed and then observed is that one can do very nice versions of these kinds of experiments using all microwave devices. So I mentioned before that the harmonic oscillator wasn't that much fun when you only can push it with a classical field. You have to introduce some nonlinearity, but if you have like a single qubit that's in here, you can do things like generate single photons on demand. You can make all sorts of non-classical states of light inside your cavity. You can also do very useful things like suppress unwanted processes like the spontaneous emission of this artificial atom. And so, that launched quite an interesting vein of research here for many years. One of the big advantages was that, and I think I won't go into the details, it was easily possible in this microwave superconducting circuit version to get what's called strong coupling, where you can go back and forth between the two components, the artificial atom and the photon, which is a microwave excitation stored in this transmission line, many times before the sort of characteristic decays of the information or the energy. And here's a version of the chip that realized that. Here's the team, the entire team that was working on Circuit QED back in 2004. You'll recognize some of us. Any of you who were at the Gervin Fest heard about how Steve sort of looks kind of the same, but some of the others of us don't. But this was a great group. Here we are standing in the shielded room that we thought was necessary, but turned out to be irrelevant for doing these experiments. And then we were, had a great time a couple of years ago. It was the 20th anniversary of this paper and the launching of this quantum optics with superconducting circuits, where we had in Marsh Hall something like 300 and something attendees. And thank you again, Florian. I'm sorry. But Florian helped arrange all of that. And so it's really been amazing to see this field grow in the scope, in the science that's been able to be done, and all those sorts of things. So there were many highlights in circuit QED over the years, again, observing sort of avoided crossings between transitions of one of these superconducting qubits and a cavity or an oscillator mode, being able to exchange back and forth and create single excitations, being able to observe something called the strong dispersive limit, where for the atomic physicists, the AC Stark shift of one photon is actually a large enough frequency shift that you can resolve that in the spectrum of the qubit. So here's the spectrum of a qubit and a cavity that's got on average about 4 photons, but you see sometimes it has 1, sometimes it has 5, and the like. And there were also things like moving to a fully 3D, even larger version of this system that boosted the coherences quite significantly. One of the things that enabled a lot of this work was the invention of an even simpler qubit. It's basically the same as the Cooper pair box. It's just 2 electrodes coupled with 1 Josephson junction. You now are able to get rid of all the biases. Look, Ma, no wires. And now you have just the kind of cosine potential of the Josephson effect, which is enough, of course, to already give you an anharmonic spectrum where the energy levels are not equally spaced. And so using the sort of 0 and 1 excitations of these things, sort of a difference in energy of a yoctojoule, or 10 to the 9 10 to the 9 times smaller than the energy used in a CMOS transistor, you could store information quite well. There were lots of things that were sort of special about the transmon. It solved a lot of the existing problems of decoherence in the system, still left you with enough anharmonicity, enough of a resource that you could control things. But also, interestingly, it was something that we could not have invented had we not already had the circuit QED paradigm and this dispersive style of measurement, because this is a device which now has no sensitivity to low-frequency noise by virtue of being completely indistinguishable to the environment by any of its low-frequency properties. And so that means you can't measure it with an electrometer or a voltmeter or something like that. You need to measure it optically with a microwave probe tone and the phase shift of that. Another thing that I want to call out here is amazing progress on other aspects of our measurement technology, including the development of quantum-limited parametric amplifiers that rely on the Josephson effect. Michel and Conrad, when he moved on to Gilla, and others helped develop a lot of the technology for these things. Our own Mike Hatridge, when he was a postdoc with Michel, helped kind of us make that a standard ingredient in our experiments, and made it so that we could apply it to something where we could do an observation of what's known as quantum jumps. So this is one qubit that's being monitored. Each of the sort of little wiggly points is us determining the state of the system and watching it jump back and forth. So this is not good if you're doing coherence or you're trying to store a superposition, but it's something which took many, many years with real atoms or real photons to be able to observe these individual quantum jumps between states. And it's also kind of a prerequisite for being able to do things like error correction and the like. With this circuit QED platform, we did in Becton some of the first algorithms on quantum devices. We had this electronic processor, and we did both of the algorithms you could do with that 2-qubit processor. But nonetheless, we could sort of show that this platform was, had the potential to operate as a rudimentary quantum computer. And I think it's true to say that most of the industrial efforts that you may read about out there are, at least with solid-state devices, are pretty much brute force extrapolations and expansions on this kind of paradigm. And here you see some of them, like the Google Willow processor, things in China, IBM, and also in academic groups. I should leave some time for questions, I guess. So maybe I'll go very quickly through one last thing, which is kind of, I guess, a little bit of the perspective. Today we actually have the ability to make collections of hundreds or thousands of superconducting qubits on a single chip and control and measure all of them. The ability to manipulate these things has gotten quite good to the point where we can do hundreds or thousands of operations. But we still don't have like a useful computation done by any of these machines, nor do we have a fault-tolerant or a really robust way of making these quantum computers. And one of the metrics here for sort of how good or how interesting your quantum computer is something called the quantum volume. It's basically how many of these qubits, 2 raised to that power, that you can really entangle. And I think the current record is still about like 10 or 11 for superconducting qubits. For trapped ions, I think it's maybe in the 20s. And you really want hundreds or thousands of qubits to do interesting computations. What's needed for that is a way to do error correction. And I won't have enough time to really go into this in much detail. But one of the other things that we've had a lot of fun with in the last 10 years or so is a different direction for how to store the information that we think offers maybe a more efficient path to making robust and error-correctable quantum computers that would really be useful for other kinds of applications. And the idea is to basically flip the paradigm of circuit QED. Instead of having the cavities or the oscillators being the thing that you use to protect the qubit or measure the qubit or whatever, you say, no, the qubits, the Josephson junction containing devices, those are the input-output and the control actuators, and I'm going to actually store all the information in one of these linear cavities. And there are reasons to do that. Basically, they are simpler systems that have a kind of natural hierarchy in their errors. Oops, that's not what I wanted to do. They will always, I claim, have better performance than a Josephson junction containing device, basically given what we know about materials imperfections and the way we have to make these kinds of circuits. In 2016, in Becton, we did an experiment using a 4-component Schrodinger cat state of a cavity. So it's something which is a superposition of plus x and minus x as one of the states, and a superposition of plus p and minus p as the other one of the eigenstates that is storing the qubit. And it had the advantage that you could detect in real time, without messing up the information you stored, when photons were lost from the system. And that very simple system, using just one cavity and one transmon, was used to sort of perform an experiment that just barely started to improve the lifetime of things a little bit. But what you really want is something where the gain you have in sort of the performance of your system due to error correction is a big number. A more recent version of this, bosonic error correction, done by Vlad Sivak and Michel Devoret's group here at Yale, got to a gain of 2.3. The record right now for multi-transmon devices is an error correction gain of about 2.4. So we have a long way to go if we want to make systems that are really robust and have large advantages. But it's now a really interesting time in this investigation of quantum error correction, which is kind of a whole other talk we could give, in which theory and experiment now make really interesting and useful contact. And so with one of our colleagues in applied physics, Shruti Puri, inspired by work she was doing with folks on neutral atoms, another approach for doing quantum information processing, she kind of taught us that detecting the errors was maybe a way to make full error correction a little bit easier and more efficient. And that led us to think about, well, hey, maybe we can encode a qubit as a pair of cavities that are sharing one excitation, one microwave photon between them. And that could give us, we proposed, a really nice hierarchy of errors. This is only a few years old, this concept. It's already now in commercial systems that are being developed by now D-Wave, the parent that bought our startup Quantum Circuits, Inc., and has demonstrated very high performance gates and operations, the point of which being that in some of the systems that they are now able to produce, you are something like factors of several or even tens below the threshold at which this error correction really takes effect. And so the idea is that you might be able to get error correction gains with this kind of qubit that are even bigger than 10, let's say, which is something that really, when you now scale up your error-corrected system, would sort of make some sense. So it's been an amazing time. It's been a lot of fun. We've also trained a lot of folks in interesting ways. This was the group that did the 2-qubit entanglement experiments. We're doing the 2-qubit dance of sort of showing a Bell state or something with our spin up and our spin down. I've given the sort of lightning version of many of the highlights of the field in this last couple of decades. All of this comes, of course, from having really talented people who are excited about doing science and seeing where it will lead that come and work with us, and that's been an incredible pleasure. Thanks to all of you who have contributed to this field. Maybe just by way of summary, it's a really nice story, right? I mean, the field did start 4 decades ago with pretty much people trying to have a new way of attacking an old and fundamental question about the basic structure of quantum mechanics. And we didn't exactly know anything about where it would go, but this has turned into superconducting circuits, a really great kind of playground for performing experimental investigations of all kinds of phenomena. We can do things that you can't do with real atoms and real photons due to the control we have over these systems, and maybe also an emerging technology. And I also want to make a point that just because something is now 40 years old and seeing a translation into the real world maybe, doesn't mean that the time for innovation is over. As I sort of just briefly sketched, like we've sort of been reimagining even the basic way we make the qubit in the last couple of years. And so for all of you young people, students coming up, I hope you'll have as much fun as we've had, and that you maybe consider adding your insights and your creativity to this field. And we'll see where it all goes. So thank you very much.
Companies that are going forward with this, ever had Microsoft? Fundamentally different, or?
Right. I was listing companies who are doing superconducting devices as their main approach. So Microsoft has both a theory and an experimental effort. They are mostly focusing on something called Majorana qubits, which are supposed to be inherently robust. and have never been observed. That's a fundamental particle we don't know if it exists yet, and they're working on it. Intel, for example, is working on semiconducting quantum dots where you can make qubits and all sorts of stuff. So there are many other approaches out there, but it's kind of interesting to see, nearly all of the big tech giants having at least a toe in the water on this field. Others?
Other questions?
You talk a little bit about the collaborative process and how that's benefited you and Yale.
Yeah. So I do think that our superpower over the years here at Yale has been that we are small, but we take advantage of that small size by being extra collaborative, extra interactive. So, Michel and I had our offices just down the hall from each other. For those of you who know the fourth floor of Becton, where most of these labs are, we also have this little alcove with a blackboard where people are always discussing physics, and people are always walking up and saying, "You're wrong," or "Oh, that's a great idea." We even had the advantage of having, like, Steve have many of his postdocs located there with us. So, like, co-location and a critical mass of smart people is really, really great. We're really looking forward to what kind of things can happen in the PSEB, in the new building, once all of the quantum efforts from across campus are going to be able to be centralized and sharing a coffee machine and many blackboards. I think you never know where these things are going to go, and you have to just kind of pull on strings in research. When you tell the history of something, it makes it seem like we knew exactly what the next step was and what the next step was and what the next step was. And that's not at all clear. Usually you're very confused, and you have an idea that maybe if I step over here, it'll be a little better. That's how science is done. So. But yeah, it's been great to have this team.
What skills or knowledge do you have to be productive in building qubits?
That's a great question. So what skills or knowledge do you have to be productive? So this is an interesting field, right? It's a little bit computer science, it's a little bit electrical engineering, it's a little bit physics. All of those skills are useful and valuable. I think the most important thing is willingness to learn, right? Because, again, when you're doing research, one of the fun things is you don't know what next piece of information you're going to need to acquire in order to get yourself unconfused. But, a preparation in the basics of physics is never going to hurt. That's our core business, after all. I think it's really interesting to see people from computer science, electrical engineering, and other disciplines getting involved. Material science as well, because making better widgets is an important thing. Radio astronomy, which is kind of where I came from, but yeah.
Quantum certificate,
Oh,
you can teach about.
yeah. Maybe Steve can speak to that.
Sure. So the Yale College now has a certificate program, and we have a skills-based certificate in quantum science and engineering. Students take one of two core courses plus some additional number of other courses, not entirely in their own major, to try to encourage the sort of interdisciplinary training that on the Y2Y webpage if you're interested.
Mm-hmm. Yeah.
Can you talk a bit about the involvement of industry in all of this and how you navigated that at the beginning and how you navigate it now?
Yeah, so it's an interesting question. So, as a physicist, I think when we started on all of this, we didn't really have an idea that it would turn into an industrial activity. Usually in physics, like, you think that's for, your grandkids' generation or something, is when your physics is going to translate into real technologies. But I don't know, think about the transistor or other things like that. I think partly because of that mindset in physics. Some of our colleagues have this kind of view that things are all or nothing, that like you'll be doing an experiment in an academic lab and then like it'll work in some way so that, you know, like you break glass, pull a lever, and, you know, industry comes in and swoops up and turns it into a product. And that's not the way it goes, right? You know, there was a period of time where some of our physics students were like, well, this is all going to be over now because this is like 15 plus years ago. Now industry is getting involved and they'll just take it from here. And the thing I would say to them is like, well, when did academic research in semiconducting devices and materials cease as a discipline? You know, we stopped in the academic labs like competing with Intel on how well it can make transistors or directly making better CMOS transistors, but we were exploring all sorts of other kinds of things. So I think, you know, we're now in a stage where that's a little bit better understood, and, you know, having a vibrant academic and, you know, basic science component that goes with a commercialization component is kind of important, because I guess one of the things I've learned by being a little bit involved in the industrial side is there's no time to indulge your curiosity or to try something that might not work. You have to basically be only working with components you think you understand very, very well. You're reducing it even further to practice and trying to get a large team to build a complicated thing. And there isn't time to try a wacky new idea. But, you know, at the same time, you can't have like a staleness where there are no new ideas hitting the floor of industrial labs, or you never get there, right? So I think it's been an interesting thing to see. We'll see where it goes, but I think there's now a decent balance between the two.
In the historical part of the story, you described how there's this breakthrough experiment, the Devoret, Clarke, and Martinis one, and you said that then people kind of walked away from that as a new tool, as a new discipline, as something to explore. Why did that happen?
It's not clear. That sort of predates my arrival in the field. And no. No. But where I was going with that is I've asked people like Michel or Steve, I guess, who have been around longer. High TC did happen in 1986. There was a lot of work on squids and superconducting devices for a variety of applications in geophysics and other medicine and things like that. So there were lots of applications that were being studied, but these exotic quantum effects that happen at millikelvin temperatures, the focus really was on, can I understand it from the single particle level up? So kind of looking at things like weak localization, as one electron splits up and interferes with itself as it scatters off the impurities in a solid or something. And I'm not sure that the idea of quantum computers is exactly the whole reason that this came back as a big thing, but I think it was also realized that there's a lot more interesting things you can do now with these devices. Maybe also technology advanced a little bit. But.
Maybe I could add a little bit.
Yeah.
I was around a little bit before your time. There was this feeling that macroscopic quantum effects was a fringy activity, that was sort of like a little, because Roger Koch was doing this at IBM when I was there, just after I left, and it was kind of, okay, but, why is it really going to matter? And I don't think, all those people that were thinking about these more fundamental things were still looked at as kind of fringy and kooky. We also had Charlie Bennett there doing it, but it wasn't anybody's. You weren't going to make your, career with it. And
maybe, one other thing was Leggett and his musings. He didn't propose a falsifiable theory of quantum mechanics breaks down when this number exceeds 10. And so you could look
Looking.
for, a breakdown of quantum mechanics at the macroscopic scale, but like, where's that going to happen? And without a good guide for that, like, how do you do a good experiment?
Not a thing you vow.
So that's maybe one reason it was kind of crackpotty.
Kind of considered just kind of kooky.
Or trivial, if all you're doing is making a weak version of, an atom.
Trivial because I think none of us understood nearly as well as these guys. Some did, but most didn't. That you're really quantizing a circuit. We still thought it was sort of superconductivity, not the fact that you were quantizing a circuit. And now, of course, I remember all the condensed matter people. What are you talking about? Let's look at the electrons. Let's look at the whole Hamiltonian. Why are you quantizing this phenomenological thing, right? So there was that, for sure.
Well, there you go.
I don't know, Leonid was around for some of this.
Yeah, I disagree with you, actually.
Okay.
Yeah, there were experiments of, I think that actually it was, part of it is that technology just grew to the proper level, because after this experiment, there was this great experiment about the first Devoret Martinis Berkeley paper, this decay of the quantum state. And then there was this thing, this so-called quantization, which Rob mentioned, of these broad levels, and you can take it as a grain of salt, okay? So then people tried actually to look at the coherent oscillations, and Jim Lukens across the strait of water. He tried to do it for years, and it never worked. And it never worked because basically the dissipation was too high, which is this RSJ model. This reversal RSJ model was killing him. And only then later on, Sakme developed proper technology, and then Nakamura picked it up and perfected it to see very short time scales. And then these guys came and just said we can just cut off the wires and use microwaves. So that was basically, I think, the main thing that happened.
But Nakamura was very late, like 98 or something.
Yeah, but at the beginning of the resurgence.
Decade in there.
Yeah.
But that took time, to develop basically the Cooper pair books, the Coulomb blockade, also mentioned at the level of 2E rather than something else.
Sure.
And then seeing with the electrometer that indeed superconductivity matters in little things about just the Cooper pair books. It's incremental. I mean, I don't think that was not just.
But the single electron stuff was very classical, right? No superpositions and so forth.
Well, that's not true actually, because if it's superconducting Cooper pair books, it's a Cooper pair books. It's not. It's not that classical.
All right. Any last questions from the students, or shall we just get them some gloves and have them come up in the front here?
Last question. I suppose this is mildly related, but as far as the development of technology, I suppose 50, 60 years ago, maybe you had to make your own dilution refrigerator. Now you can, buy one, but then maybe you had to make your own cryogenic components, but now you can buy them. And we used to piggyback off of all the telecom industry and buying our electronics, and that's part of why we might work at certain frequency ranges. And now there's sort of a developing little industry of electronic devices specifically for quantum applications. And okay, maybe a good ways down the road, there's companies selling full quantum computers.
Right.
Is there any clear additional intermediate step you see as far as like a company that like right now everyone has to make their own blank because it's there's not a big enough market, but maybe 5 years from now there's a commercial blank that you can buy, or are we kind of
Here you start, you have a need.
Yeah, I mean, it's a good question. I mean, you used to indeed, kind of have to build nearly every widget in the experiment yourself. You saw the photo of the Berkeley one with the filters and everything. There were still some SMA connectors that were commercial there. It's not clear to me. I guess, in a lot of science labs or physics labs, they're pretty sophisticated pieces of, technology in the form of oscilloscopes or the like, and I don't know what all of the sort of, on beyond versions of that there are that enable more work on this specific kind of quantum thing. I mean, certainly, it's gotten harder as you make the systems larger and higher performance and more complicated, but we're also getting better at the way you do all the parts, and you can outsource more of it. So, yeah. Okay.
Thanks, Rob, again.
It's too bad I didn't know the stage where. Well, I didn't mention this way. His father has this. He's quite wealthy. He might be able to come. Yeah. So I'll ask him that. And I'll explain it. It's not a reflection on his quality. I'm glad you understand what you can help out with. Okay. I hope that'll work.
I make sure the chalk on this, it's good, it's no more batch. It's like, oh, maybe this.
I never understand.
Oh, yeah.
Well, I was really obviously, you know what I mean? The first like 5 minutes, and then they get into their own. But everyone's I went back this year. Oh, you did? Yeah. That's perfect. I couldn't. So funny because I went to Italy for a conference. I'm also waiting to get March. I'm now
Oh, good. Yeah. Is that fun? Yeah.
So that means
He's one of mine. Oh, no. I don't have a half a million. The investors have a half a million. Oh, yeah. No, I did ask Michel about this item. I heard that Michel was wanted to do this experiment and went to her and was supposed to do it. And then I asked Michel his thoughts on this, and he said, no, I wasn't at all sure what I was going to do.
it's very, very, very.
They're still treating as if it's like outside.
But I still think so actually one of the things they found
Sort of observing the quantum
bigger and bigger quantum
processes.
and they never stopped being quantum. You just have to do the experiment.
I think that was the same time, or maybe
Never anything.
I suppose there were ideas for it. Michel did know he wanted to work the circuits and learn about superconducting. A group of African.
I'm actually a reporter for Yale.
Neil Sullivan. Yeah, I was going to say Neil Lane, and I'm like, that's not right.
I think he gave you the lead. The lead is, hey, it's a nice thing to do every year. So.
Okay, well, big talk, and they're saying
I mean, it's quite
look at the old draft too, and say,
And B, it's really extraordinary. One.
Yeah. I know. I think the seeing the energy levels
is better for sure.
Rob also is a huge leader.
but that could also be.
But also, was it,
Another thing that's
I said, the orange,
somebody in physics or applied physics started a company that sold for.
Yeah. Petrovsky, that one is active.
Petrovsky's all classic.
oh, yeah.
The only
Anyway. Yeah, but but just looking for the existence of the three. But, yeah.
You know, the I guess the other ingredient is that the energy levels were observed to move around as they should, according to
When they change the conditions
of
of
the shunted junction.
Yeah.
So, you know, there's a lot of these things like we don't really know.
Oh, so Landon Glassman is pretty much in the same field I was in. I was also working on the small.
There was an interesting
systems,
debate
in the same time frame. Two show quite well. And in '87, there was this field of mesoscopic physics, which was much bigger than a single atom. Small. And so
I had one of my students do it. Oh no, I mean I had a student from my micros class do this.
he would, I think we don't disagree very much. He was saying there were people trying to build on it. So hard to do.
Do you have to violate Kelvin's inequality with people?
So it was like 17 periods. Exactly.
That's hard.
Right, and you know the
Do
answer
you call
is
that the unauthorized
it took
use of
people
bells of the column?
right making a few copies of
And
you know,
so
slightly
at that
different
time it was
versions
dead.
of the system.
He came from radio
With
school.
different quantities and seeing
And
they
yeah,
all
but there wasn't any big advance. And then
match up with
is this very surprising, exciting
Hamiltonian
thing.
describe all of these.
Japan had started to show better coherence in quantum behavior. You could manipulate Josephson related sort of computing technology.
Yeah, yeah. I mean, so that
Shor,
I think that's the kernel.
94, 95. Peter, did you learn the name Peter Shor?
Right. So the subtle point is
Okay.
that
So
phase is
that's
when
I'm gonna go. All right. Well, one sentence. But if you want to hear, I've given two talks, both available on YouTube. One is called Why Should You Ever Learn Computing?
exchange of
But basically, there was a before Shor.
was identical or not?
Yeah,
that doesn't exchange interaction.
That's one
around
with it.
things like,
But they still couldn't find anything
observe that Purcell effect.
to make money or to make whatever economies or excursions. And then this guy Shor proved that you have ideal quantities standard choose for encryption. 90% of
I guess there's a line I was going to use.
and this was believed to be unbreakable because of the mathematics.
Conrad and I would give some of those
Solve it couldn't be done. So suddenly,
here's how
oh, this is a national security issue.
plain was
Secure.
a system.
We're gonna be able to.
And then at some point it evolved.
Maybe it's gonna let us do even more nasty
Hamiltonian
wonderful
real
things.
Before really meaning
Anything that was
Because it does like
manipulated.
switch turns on.
I don't know. There was a guy
Which was gonna be.
Ricardo was over here.
And when you say this audience was mostly graduates.
Yeah. No, it was a good mix, but it looked to me a lot of undergrads. Yeah, I think all the physics majors came. I gave this lecture 3 years
Great
ago.
job.
Hi, my name is Anya Grace.
Oh yeah, hi.
Nice meeting you.
Nice to meet you in person. Yeah.
Yeah,
How are you doing? Oh, good.
I was
Awesome.
wondering, what is like
That's basically how it's being. Or sort of, people believe that it's like, they believe it, and that's like, your explanation will like it, and the lawyer, just like the alternative hypothesis is just really science.
It's actually, I realize this because I recently read the 37 paper, but it's very analogous. Because in both cases, like, we described spectroscopy as we switch the frequency, right? But it was hard to switch the frequency. Yeah, I get the frequency fixed, and they sweep some DC bias. So, like, in the other experiment, they're like, sweep the tilt angle between the intermediates of the levels until it runs into their drive that's always on. So, like, instead of picking their drive and sweeping it, they like keep it fixed and then sweep the energy level until it runs into it.
Well, describe that exactly. So it's not actually changing the frequency, they're changing the current.
And actually probably did the same thing. So he has a big static B field, and then he's got a little RF field, and he can't sweep that, but he can know the frequency very well, and then he can sweep the big Helmholtz coil until the levels the Siemens play runs into its RF, and then you can see like there it is.
In fact, this whole thing right, is like very hard to get really frequency flat projection microwave to requires that. So yeah, no, but it was like so much more to understand how to much of the there wouldn't have been like carefully constructed microwave. There was just going to be some metal motor with like a cracked cable with the semiconductor stripped out and no one particularly carefully worked out what the box were anyway. It was like I don't know, large like stainless steel screws and wood metal. Like the shape was just crazy. So and then like probably there wasn't all that much care for the cracked cable from like more control for anyway. And so there was an extra standard like anyway it took like really beyond the I call it. So I mean, I did this from my age. And it was just it was very routine technically, but in a way we never be all frequency class. It wasn't until like I came here and I was really strong in your transmission feature cuts actually much faster. I'm sure that was like John Clarke's we found some place where you